Welcome back. So we're going to go through all of this, conjugate priors, one more time. So I like to repeat myself. I'm going to tell you about data distributions, and maybe that's really where I should start, but let's just review the definition of conjugacy, and we'll jump back into the example we've been staring at. Conjugate priors. Somebody want to throw out the definition for me? For epsilon? What's a conjugate prior? Zach?
Any quick pages, the like prior that you can use that will give you a posterior, same thing?
Yeah, exactly. So the prior and the posterior belong to the same distributional family. Then the prior is called conjugate. That's it. So what do you have to stare at to understand what it is? You stare at the likelihood and kind of imagine what you would multiply through to preserve its form. It has the same functional form in the posterior and the prior. So you're really just thinking of what's the posterior, you're updating it. It's the same exact thing, it's the distribution over the same parameter set, you just learn through the data. So it's a sequential update to adapt learning from the data instead of just what you think before you see the data. Of course, I've said it in that way that's kind of controversial and cites a lot of fights. What do you mean, things you think before you see the data? I don't really know exactly why that's controversial. I remember reading the definition when I studied this for the first time, and I was like, what's a Bayesian? And it's like somebody that uses prior information. And that's like the Webster's dictionary definition. And it's like, doesn't everybody do that in some sense? How would you build your model? So what would you do? You mean you just know nothing and it's like you're just blind? So that can't possibly be the case. That can't be the distinguishing thing. So it's the way that they use it. So I don't think that's a good definition of a Bayesian. That's obviously a good way to upset everybody. So I think a Bayesian, a good definition, let's just write this down. Definition. And you can come up with your own definition to being a Bayesian. Let's see if we can agree. A Bayesian, that's the definition we're going for. What do you think we could say a Bayesian does? So what's a good way to explain a Bayesian? There's a lot of types of Bayesians. I don't know if you know that as well. And some of them will argue with each other. What's a Bayesian? Somebody who uses prior information is just not a good definition.
They're trying to learn about the parameters, so they're treating the parameters as sort of random.
Sort of, like totally.
Oh, yeah.
Yeah, exactly, right, exactly. So they're putting the probability distribution on the parameters. So that's a good sort of insight. All Bayesians do that. So I like that. And they do a little bit more. They do that through Bayes' theorem. So they use Bayes' theorem so that they can learn about the parameters by invoking a probability distribution. So I would say a Bayesian uses a posterior distribution so this thing right here is just pi theta given x, and it's proportional to the likelihood times the prior. Prior likelihood, and this is the posterior. So it uses the posterior distribution to place a probability distribution, I'll say PUT, over unknowns. So this could be anything. So it doesn't just have to be the model parameters, but in a parametric setting where you have complete data sets, the only unknown to you, given the data, are the model parameters. So I'll say this is a little bit more general, than just talking about the thetas. This could be for like missing data or something like this. You could do this on anything you didn't know. So you could say, okay, I've got this form of the likelihood. There's parts that I don't know. If I multiply by a prior distribution on those things, multiply it into that likelihood function, update the unknowns to random variables. That's what a Bayesian does. So any unknown in the model, if they end up putting the probability distribution on it, they're a Bayesian. So I would even go as far to say, if you take the likelihood function and you magically upgrade that to a probability distribution, you are a Bayesian and you just multiply that likelihood function by 1. So you're effectively a Bayesian. Now, if I would have said that in the 1940s and Fisher was in the room, oh no, you know, why do we have to fight about this? So he had another branch of inference that he called fiducial statistics. And it was this magic wand that he said, well, I'll just take the likelihood function and I'll upgrade that. And I'll use that to model probability distributions on the parameters. So I'm going to just automatically upgrade everything to a random variable. And he said, because it makes sense. So he didn't have a real argument for that. And people tried to defend it and understand what he was doing. And unfortunately, Fisher said, no, I'm not a Bayesian. No, absolutely not. You call me a Bayesian again, I'll call you a fool. I'll write about it and we'll fight about it. 20 years later, Fisher said, okay, maybe it's like this. So I just want to remind you that people's opinions adapt, they change over time, and just because somebody said something once upon a time doesn't make it true or well established or agreed upon. So again, I think that this is all just very formulaic. This is like just a functional form of things. It kind of makes sense, but there's a bunch of philosophy involved, and sometimes that can be helpful and sometimes it can be distracting. I like the philosophy. I think it's a fun game to understand what people are thinking about and what everything means. But at the end of the day, I would say if you effectively just turn this into 1 and you said the posterior was that, if I did describe it that way, that you're multiplying the likelihood by 1 and I'm auto upgrading everything to a random variable, I could maybe imagine that is Bayes' theorem. So I like to use the words effectively speaking, we're doing the same thing. So you'll see people that say I do inference off of just the mean and the variance, and I use those two forms, and I place intervals on things by looking at the mean plus or minus 1.96 standard errors. You know, that has something to do with the variance. And I would say, oh, you're assuming everything's normal. And they go, no, I'm not. So there is a branch of statistics that does that, and they adamantly say they're not invoking normality. But I like to say, but if I did and assumed everything was normal, you would get the same answers, right? Think, well, that's true. So, but that's not the way they think about it. So there's lots of ways that people will think about things. So sometimes you have to be practical and say, but if I thought about it this other way and I got the exact same answer, aren't those kind of equivalent in some sense? And I think a rational person would say yes. Saying that, not everybody's super rational, so it's a matter of taste. But a Bayesian always does this. So they put a probability distribution on the unknowns in a parametric setting where you have complete data sets, that's just the thetas, and they operate under Bayes' theorem. That makes a Bayesian a Bayesian. So that's what it is. So people that are fixing the data sets and calling whatever that function is at the end of the day, this penalized likelihood function, and calling it a probability distribution by normalizing it, that is what all Bayesians do. So I will kind of point out the different branches of Bayesians. Think about that a little bit differently. So we kind of talked about there's people that don't care what the prior is. It's just a set of knobs and levers, and all we care about is establishing good inferences through the posterior. So you can kind of back that out and say, what would the prior have to be to get certain properties? And I think objective Bayesians think that way. So subjective Bayesians, the super subjective type, just say, well, I feel something about theta, or they couch your scientist and through some battery of questions, you're able to elicit, it's a good word, elicit their prior distribution. So I will point out, I've never seen anybody do that really effectively, and I see a lot of people say we're eliciting a prior, where it's like, you're not eliciting, you just wrote it down. So that means something different. So you hide a lot of things behind fancy words, but at the end of the day, all Bayesians are doing inference off of posterior distribution. Posterior is derived through Bayes' theorem. So that's a little bit different than what maybe the Webster's dictionary will tell us. Just since we're playing this game, what's a frequentist? There's these branches and camps. What's a frequentist do?
You just think those unknowns are some fixed number.
Okay, fair enough. So they might think of it as some fixed number. I would say, I'm on the same page. I might think that the true value of theta is some fixed number, but I'm using a random variable to measure what it is, and I'm measuring my uncertainty. So we don't even have to argue over that. But I've heard people say that people say, oh, the whole Bayesian thing is void from the onset because if theta were fixed and you're treating it as a random variable, well, that doesn't make any sense. Usually I say, well, that just means you don't know what a random variable is. I'm not saying that it's random in nature necessarily. I'm just saying that I'm using a random variable to measure its probability. It's unknown, it could be fixed. If it was variable, then this would encapsulate that. But if we were fixed and unknown and are trying to measure it with a probability, then that encapsulates that as well. So I don't think that's the end all be all. If it were fixed, I can't think of it as a random variable, because a random variable, bless you, doesn't say it's random in nature. It says that there's this mathematical thing that makes it a random variable. So random variables have certain mathematical properties. So they integrate to one, Kolmogorov rules, so that sort of thing. So it's a little bit different than a variable. It has special properties. Anyway, that's what Bayesian does. And I think a lot of the arguments could be obviated just by saying, okay, well, what's the performance? And let's do a comparison. And before computers and doing comparisons, everybody argued just basically off of philosophy. And that got us so far. But now I think now we can actually combine results with philosophy, and I think that's the holy grail. Okay, so here's another definition of a conjugate prior. Have the property, so I'll call this pi theta. If both pi theta is an element of f and pi theta given x is an element of f, and this is just a distributional family and they're the same families. So I'll just call it the same dist and just get rid of the word family because sometimes people confuse that. So it's the same distributional, maybe type. Then pi theta is constant. So pretty easy concept. And then of course we have that model structure, how we get those things, because we're talking about a Bayesian analysis, that the posterior and the prior are related to each other through Bayes' theorem. So frequentist, again, what are they? Because I've heard these, and I'm not saying they're incorrect, and I'm not saying that you wouldn't have gotten an A+ in your classes by giving those answers. They appeal to some people, but I'm like, man, it's a little not there. So random variable, random in nature, totally different things. So we have random data. I don't know what the parameter is. I like this engineering utility of a random variable. Somebody made up a definition that seems useful. I like it. Okay, there's theory where I can maybe convince people it's more rigorous than all of that. I guess that's a big deal to maybe 4 of you in the class. I like to distinguish these things, but at the end of the day, it's just this. So for a Bayesian. But what does a frequentist do? We hear the word, I hear people say all the time, I'm a frequentist. Okay, tell me more. What kind of frequentist are you? You know, and then when they're like, I just mean I'm not a Bayesian, it's like, okay, right. So Michael?
Yeah, I was thinking, we did depend on long run science.
Yeah, so probability is kind of viewed as this long run average sort of thing. So X bar is approaching P in the binomial example. So it's this long run average. So that's the relative frequentist. So that's a particular type of frequentist, relative frequency. So you're maybe invoking some asymptotic concepts, and maybe you take a step and you become the asymptotic frequentist. There are exact frequentists that will give you exact probabilities. So there's also conditional frequentists where they condition on ancillary statistics that we'll get into in chapter 6. Nobody knows how to build that paradigm up exactly, which ancillary statistics you condition on. I'll point out that a Bayesian conditions on all statistics because they condition on the data. So they've conditioned on all the sufficient statistics, the min sufficient statistics, the ancillary statistics, and everything. So the Bayesian gets something for free. We'll talk about a few examples to maybe clarify that. But the point is there's a lot of frequentists out there, and before you say you're a frequentist, you better know what you're talking about. Well, okay, you don't have to know. So you can be like everybody else. But I think that it's important, if you're gonna say you're something, know what it is and know what it's not. So sometimes I have to think through that a little bit carefully. That I don't know what something is until I know what it's not through something to compare against. So that's where I think a lot of these definitions are a little bit vacuous. I think there's some notion of relative frequency or some frequentist notion for a probability, and it depends on what you're doing. So for example, a confidence interval, this notion that is I keep collecting data sets and I build intervals out of those individual data sets, some frequency of those will cover the true parameter at some nominal rate. So a 95% interval, maybe it covers the true parameter at rate 95%. So for the normal sort of thing where we take X bar plus or minus 1.96 approximately, it's not exactly that number. Sometimes we round that number to 2. So approximately 2 standard errors out. Those intervals, if the data was normally distributed, are exact covering. And in fact, the Bayesian would derive that using a flat prior. We'll look at that example a little bit later. And so the Bayesian must be an exact frequentist too, in those sort of examples. So all of these, it's more about properties and which properties you have and you want to guarantee that you have. When I see people say, when they say I'm a frequentist and I use this asymptotic interval, and it's like, well, how well does it really cover with like the 42 data points that you have for the problem that you have, or 42,000 data points, but you're in a 50 million dimensional space. So it's effectively the same thing. It sounds really impressive, but it's like having like 12 data points, you know, in a one-dimensional example or something like that. And I ask them, how does it actually cover? And they say, well, here's some asymptotic theorem as n goes to infinity. I'm like, no, I want to know how it covers in your exact case. So for the binomial example, if I invoke the normal approximation, it doesn't cover exactly 95%, and it actually depends on what P is. So P closer to the middle, those intervals are better. P closer to the endpoints, the intervals are worse. And so if they say they didn't check, and they say they're a frequentist, I usually just think to myself, okay, you're no frequentist, so because you didn't even check. So you're just using some guiding light theory. I would even question whether or not you're a real statistician. I would think that you're a probabilist at that point. So, and that's fine, if you're in academia, they're allowed. You know, we need those people too. So anyway, try to hone in on these definitions when people tell you, I'm a this. Because I bet they're more than that and they're not being precise. So my point is that a Bayesian could be a frequentist, but we need to check the properties of something that's happening in terms of some sort of frequency. So they're not really well defined, and I think that's where a lot of confusion comes from. When people ask me, what's a Bayesian at a party? I'm usually thinking this is going to kill the whole conversation. This is going to kill the party. So I'm usually just thinking, well, it's just a group that places random distributions on unknown things. And you'd be surprised other people don't do that. And it's a relatively simple thing. If they ask me for an example, I usually tell them later. You know, kill the conversation right there. But so just to distinguish, a p-value is very different from that sort of thing. And so we're going to get into it. But the p-value is, I'm going to look at data more extreme than what I've observed under some fixed null hypothesis. So you're not placing the probability distribution on the parameters that you're interested in testing in the first place. So it's a totally different thing. So what did you put that probability distribution on? It's not on the hypothesis itself. So operationally very different. What a p-value does if you threshold it is it tells you something about error rates. So you're protecting error rates, which is a very different thing. And I would say a Bayesian analysis could be calibrated to error rates too, by thresholding decisions that you get out of a posterior distribution. So a lot of these things do have overlap. That's what I want to kind of point out. So they're operating procedures. So I usually think of this as the Bayes operating procedure. Likelihood times prior. It's just a format for doing things. And there's lots of ways you can think about it. Okay, so we've got some definitions. A few notes for the future. So review tomorrow, quiz on Friday, homework due Friday, midterm a week from Friday. I will point out with homework, you have a homework due on Fridays. And then I don't think I make the homework due until the 15th, and I just give you a few easy problems in chapter 6. I want you to do them. So they shouldn't take much time. It's meant to be easy. It's like a 2-hour homework assignment, but I am going to test you on sufficiency. So next week. So those problems will take you through it. I'm not going to ask you anything overly challenging. I want to present you with those concepts through probably Monday. We'll start it on Friday, get through most of it on Monday. Do something on Wednesday, kind of recap, refresh, do a review session on Thursday, and then take the exam. So I do want you to do those problems. I just don't want you to be bombarded with having to write them up. So don't procrastinate on those. They'll help you. Okay. Talk about beta distributions. Everything. I'm always depressed when I drop my chalk and break it. This is the punchline to that beta or the binomial or Bernoulli problem, how you think about it. I'll say a few words about that. This will be our underlying example that I'll use for motivating sufficiency. So the two experimenters debating with each other in the first part of chapter 6. I'll use this example. And they have another example that's a little bit harder. And I'll discuss that example too. Okay. Beta. This. Really what I'm going to show you here is the density function. The dist itself is the probability measure. Just to distinguish, but there's a 1-to-1 gap between these two things. So they look like this. So I'll just say Fz. So I'm not doing anything Bayesian. Oftentimes I use the letter pi when I'm doing a Bayesian analysis. I'll say a little bit more about that in a minute. But this is just some distribution. So again, this is kind of a side, just extra stuff, so I like to invoke a different random variable. And this has two parameters that underlie it. If we were using this as a prior distribution, we'd call those hyperparameters. But if you were just writing down the distribution, we'd just call those parameters in the analysis. If you call them hyperparameters, people would go, oh, you're setting me up for a Bayesian thing in 2 seconds. So these are just underlying parameters. So when I let those be variables, I have a whole family of beta distributions, and when I plug in an actual alpha and a beta, I have a specific beta distribution. Hard to distinguish on the chalkboard. I'll write down the important part first. So there's a normalizing constant. We're not going to get too much utility out of that thing in this class. So I want to focus on the important part first. This is p to the alpha minus 1, 1 minus p to the beta minus 1. And I should probably say a few things and be polite, that p is an element of the interval 0, 1. If you want to include the endpoints or get rid of them, it won't make any difference. So I usually just put them in. Alpha is greater than 0, and beta is greater than 0. I will point out that Bayesians love to take the limit points and throw in the endpoints and do things with them. A lot of times they make things that don't integrate to unity, so they're not integratable. That doesn't bother the Bayesian if they're interested in doing inference off of the posterior distribution. I think that's an important point, and I just don't want to discuss it at this moment. So there's more stuff that we're going to see later on, and I'll dwell on different philosophical points later. So these are just basically, they're putting weights on P or weights on 1 minus P. So this is kind of what we usually call the probability of a success, and this is the probability of a failure. So it's weighting how many successes and failures you might see out of things. So you might think of it that way. So, but this is a continuous distribution between 0 and 1. Normalizing constant is just a beta function. I'll write it down like this: beta alpha beta inverse. That's called a beta function. And you know exactly what it means because you can all find normalizing constants to everything. It's defined through an integral. So beta function is just the integral between 0 and 1, p to the alpha minus 1, 1 minus p to the beta minus 1. And some of you might know that this can be expressed through 3 different gamma functions. So it doesn't really help you with anything in this class. But that's the definition. And typically, if alpha and beta are just any old numbers, you can't write it down any other way than that. You can maybe approximate it, but if you had alpha and beta being integers, we know the connection between gamma functions and factorials, you could maybe write it down exactly. So I like just thinking of it as this function. So when we write down things and we think things are closed form, we write something like that that's expressed as an operator, it's not really closed form. So we just get so used to things that we think they're easy to analyze, and I can think about this thing in general. So since it's all one-dimensional, we can think about it pretty well. So that's what a beta distribution is. Just real quickly, what's the expectation of Z? I'll be polite and write this stuff in. I like to see it. It wouldn't be typical in other classes to tell us that it's a function of alpha and beta. But keep in mind, if you say anything to do with Z in here, that's the critical mistake that I hate the most in this class. Because this is it defined in terms of an integration over Z. So, and it's a definite integral, so there's no Z's in here. So does anybody know what this is? Yeah, exactly. So this one's pretty easy because you know this thing has to live between 0 and 1. So you do a little inspection on that, and that's what it is right there. Does anybody know what the variance is? I'd be impressed.
I take a guess. Is it alpha beta over alpha times beta? I think it's squared.
Yeah, there's a
And then
square. There's
1 plus alpha beta,
Uh-huh.
and it might be that part that's squared. I don't know.
Yeah, it's that part that's squared and the other part isn't squared. Don't worry, we won't use it in this class. So I'm impressed that you kind of have seen this. So I'll try to commit your memory to things that you actually will use and are fairly intuitive. So you know that one or you don't know it. So if I'm in class, I ask you for the variance of something, I'd probably give you the So, but this one I think is intuitive, and if you think these are the rates of successes and failures, that kind of makes sense as well. Okay, that's a beta. So let's go to what I've been calling the beta binomial example, and then I always correct myself when I say it's Bernoulli, but they're the same things. Here's our example. Say xi's. These are elements of 0 and 1. if there were elements of these were something else discrete, like green and red, I could encode those as indicator functions. So heads, tails, I could call that a 1 or a 0. So I'm just going to invoke that indicator function right away. So these are Bernoulli. Parameter P, I want to see n of those. Yes, everything is IID. So our sampling distribution, f of x, that's just our vector of 0 and 1. So this is a high dimensional thing that I'm plugging in here. When I evaluate the density or the mass function for this is just a number, a scalar. What I'm inputting into it is a vector. It's conditional on key. This is just going to look like this. I goes from 1 to n, p to the xi, 1 minus p to the 1 minus xi. Just to be clear about this. F of xi given p is equal to p if xi is equal to 1 or 1 minus p if xi is equal to 0. So a different way of writing that is f of xi given p is p to the xi, 1 minus p to 1 minus xi. So you can plug in the xi's and see. That's exactly the same thing. I like formulas like that. I can code them up on a computer, I can do math with it. When I have things defined as a set, I always have to take that and translate it to a formula. We get used to doing that. So this is just the f of xi given p, and because everything is conditionally independent. So I'm a little nuanced on that. I don't believe data is independent. If data was independent, we couldn't really forecast. So we're learning something when we're forecasting. What we're usually learning through the collection of xi's is what a p is, and that's creating all the dependence between everything. So everything's dependent on the same p. If we knew what that p is, then everything factorizes quite nicely. That's conditional independence. It's a little different than independence. Okay, so I can rewrite this. And this is just p to the sum of the xi's. If I do some simplification, I go from 1 to n, 1 minus p to the n minus sum of the xi's. I go from 1 to n. I usually write it down like that. So that's the sampling distribution for these bits of 1s and 0s. And it's distinguishing the order of everything, where the 1s and 0s come in. So it seems to distinguish what all that is, even though they might have the same probability masses. I'll point out in this formula, after we simplify everything, I don't need to know the whole vector of 1s and 0s. All I need to know to evaluate this function is the sum of the xi's. So that's really all we need to know. That's the concept that the two experimenters are getting at in the sufficiency part of chapter 6. So I don't need to know all of the xi's, but there's a big punchline that I can write this down and see the parts of the data that I cannot factorize away from the parameters. So this data is always next to the parameters, and you can prove by your 3rd grade math skills, you can't factorize that. Do you need a real proof on that? No, I'd say I learned that in 3rd grade. I can't factorize this. That's what I tell my 3rd grade instructor. So, geez, that must mean that this is minimal sufficient. Okay, we'll get there. Obviously, in 3rd grade, I didn't even know what like a fraction is. It's just a metaphor. Okay. I will also point out that for a binomial, analysis, you get something similar. So if I ended up saying I'm just going to write sum of the xi's is binomial and p I don't usually think of n as a parameter in the model, but you could do inference on it. They have a really interesting example when they talk about moment-based estimators, where they estimate n and everything goes terribly wrong. So that's just a heads up, is that moment estimators can sometimes give you good answers, but there's no guarantee. We'll see that in chapter 7. So I like thinking of n as in there. It's obviously controlling the asymptotics. It has something to do with that distribution. So I wouldn't just factorize out that n, 1 minus p, to the n, factorize it out and say that's part of the normalizing constant, because it has the action in 1 minus p. And n is related to the data size. So f of some of the xi's, we'd probably rename that and call it some other variable, but I could call it just that thing. Given p, this is going to be equal to n, choose some of the xi's, I goes from 1 to n, p, some of the xi's, 1 minus p, n minus some of the xi's. So you get exactly the same kernel of the distribution. So this part looks like this. So this is the part that connects the data to the parameters. That's the part that you can't unrelate from each other. So in this part, this doesn't tell you anything about what p is. There's no p's in there. So it's just raising this function up and down. So we've already talked about likelihoods, and we're comfortable that they're all self-relative. So I can multiply by any positive constant, and it's the same likelihood function. So while these sampling distributions are inherently different, the likelihood functions are exactly the same. So in both cases, the likelihood function, I'll say, or some of the xi's, doesn't make any difference to us which one we're thinking about. This thing is just proportional to p. Some of the xi's, I goes from 1 to n, 1 minus p, n minus some of the xi's. So nothing fancy, just basic algebra. So same exact likelihood functions. That's the part that I'm going to dwell on in sufficiencies. So I'm going to basically be explaining the likelihood principle to you in disguise. So, but we can back it up and think about it just like the two experimenters think about it as well. I want you to look very carefully at the definition of a sufficient statistic. So they give you this definition in the book, and they talk about some conditional probability being a constant. I want you to look at that very carefully and see if it makes sense to you. Because I remember thinking, what the heck is that definition? I totally get sufficient statistics in, okay, there's this compression that I have, and it doesn't matter how I rearrange this, as long as that function is the same, it doesn't really matter how I do the algebra.
Sorry, guys.
No problem. Yeah, no problem, Bob. I was in the same boat this morning, because I set my alarm for Tuesday, Thursday. I had that buzzer, and I woke up 10 minutes later. I'm happy to be here. Okay, cool. Same likelihood function. So back to the Bayesian question. So, question, what's the conjugate prior? For p, so just want to put that in, and we already know the answer. That if I multiply beta into this thing, I will get a beta back. So we'll just show that answer. Beta. This is what that looks like. Pi p given, and again, I don't care if you call it some of the xi's or the cap x. I don't care how you think about that, because it works out exactly the same. We get the same likelihood function. I usually just write it like this. So pi p given x is proportional to p to the sum of the xi's, 1 minus p, n minus some of the xi's. I need more room. So times p P, and we can write out everything if we want. So we could talk about this thing right here. I usually just get rid of this automatically because it doesn't have any P in there. It doesn't tell me what the shape looks like. I've already tossed any normalizing constant here just because they don't mean anything. It's just a likelihood function. So this is P times alpha minus 1, 1 minus P, beta minus 1. So at the end of the day, what do you end up coming up with? Since I've used proportionality here, even if I write it equal here, it's all under proportionality, so I might as well just get rid of this stuff. There's no P's in there. I haven't normalized anything. I'm just thinking about what the kernel of this function looks like. The relationship between the hyperparameters, the data, and the parameter P that we're trying to learn about. So this is P, sum of the xi, plus alpha minus 1, 1 minus P, n minus sum of the xi's, plus beta minus 1. So when I recognize what this looks like a beta. So at some point, I erased, I guess, what a beta looks like, but you know that a beta looks like this. P to the alpha minus 1, 1 minus P to the beta minus 1. And all I'm really changing the definition of is what these things are in the equation. So my prior had the alpha and beta in there. I know what the expectation is. And I've got something very similar here. I usually don't call that alpha anymore. I typically will call that alpha tilde. So my updated version of alpha. This is beta tilde. Oops. So this looks like a beta with two parameters. Alpha tilde, beta tilde. And if I wanted to know maybe what the expectation of this thing was, since I know properties of my prior, I know properties of my posterior because it's conjugate. When you hear conjugacy, you think, oh, cool, I can do the calculus. I know the answers. Maybe that's the original insight, but it goes further. So it doesn't just end there. That was the only reason we like conjugacy. We hopefully would have abandoned it by now. It's hard to say. But there are other reasons we like conjugacy. I'll tell you about those later. So the expectation of P, I like to write it down this way, given X. I probably should write conditional on alpha and beta here too. I'm just not ingrained to do that, but I could write it in if you want me to. So it's going to be a function of those things as well. This is just going to be alpha tilde over alpha tilde plus beta tilde. And that thing is just sum of the xi's plus alpha over sum of the xi's plus alpha plus n minus sum of the xi's plus beta. So we see some cancellation down in the denominator. So these things cancel each other. And at the end of the day, what we come up with is sum of the xi's plus alpha over alpha plus beta plus n. And that looks pretty familiar to us. So it almost looks like X bar, except I have these penalty terms that are popping up here. So this thing I will kind of point out, as n goes to infinity, this is going to keep getting bigger and bigger and bigger and dominate that. And the n right there is going to get bigger and bigger. These are fixed numbers in any Bayesian analysis, and eventually it will dominate those. And you have some inclination to think maybe the data should speak louder than these things right here. So effectively, the alphas and the betas are upweighting successes and failures. So that's kind of what they do in the formula. But asymptotically, this just goes to X bar. So if we like asymptotics, I could say the Bayesian's equivalent. But they're not. So the asymptotic argument is just an idea. It never actually happens. Bless you. So kind of looks like X bar, and there's some penalties. And I think intuitively we can think to ourselves, alpha and beta shouldn't be too big. So let's actually see how this all plays out. through this sim study. So that's the posterior distribution. It's a beta distribution. It lives between 0 and 1. The binomial is a discrete thing that lives between 0 and n. It takes on those discrete integers. And the beta is something totally different. So kind of looks like a beta distribution. It has the same kernel. So those are all words that you will eventually familiarize yourself with. So I wrote a piece of code. To simulate everything. And I think this piece of code is on the website. Is it there? I think so. If it's not, we can give it to you. So, but basically, it just takes in some inputs. P, true P. The only place I use true P is to simulate the data and to plot my answer again, so I can see how well this beta distribution is encapsulating true P. If you ever use true P in your analyses, you've made a huge mistake, because if you knew true P, just use it. Don't do anything to it. So that is a critical error that people make. Sometimes they get the random variable back when they do their integrations, and their answer depends on the thing that they're trying to estimate. So that is the cardinal sin. Don't do that. The other one is dividing by a matrix. I don't like that either. So we'll get you all cleared up. Make sure you don't do that come final time. There will be one person in the class, speaking inductively, because this always seems to happen, that ends up producing an estimator that depends on the parameter that they're trying to estimate. Do not be that person. Don't be that person. That person never gets an A. And I want to give all of you A's. So this could be the first time ever that somebody doesn't produce an estimator that depends on the answer. I know it sounds ridiculous, doesn't it? It tells me they're not understanding. So they're doing some math, getting nervous, carrying out the math, making a subtle mistake, but they're not understanding their answer. Okay, so what I've done is I've set this up where I can just do some plotting. So I'm going to take whatever P is right here. I'm going to take my interval and I'm just going to divide it. So everything will look continuous, but it's really just a discrete example. So, and I'm discretizing based off of whatever this number is. So I'm chopping up the interval into 101 data points. 101 points. Give us the illusion of continuity. I have some plotting controls right here. What I'm going to do is I'm going to plot the prior for you so you can look at the prior. So that's just a beta. That's what all this stuff does. Then I'm going to start simulating some data. And I'm going to pause every once in a while so you can see this posterior evolve. I'm not just going to be taking that kernel of the function, I'm going to be normalizing it so that everything sums to 1. So when I do that discrete, I'm going to do the same thing for the likelihood. I'll plot what that looks like. So we've got prior and likelihood. We can look at both of those. So that's just one of those functions that we've already written down. So param value is P in all of this. Observed is X, sum the Xi's. And this is the number of failures that we've observed. So I'm going to plot all that stuff, and then I'll normalize everything. I'll actually plug all this into the beta PDF right here. I guess I could have not used the beta PDF function and just done this myself. So, and then I'll plot the posterior. So everything else is just plotting control. So let's do this. So I'm going to pick some numbers here. So this is true P. This is going to be alpha. This is going to be beta. And this is going to be N right here. So let's pick some values. So what do we want P to be? 1. I like it. We could do it. It'll work. So it won't be super insightful in the last minute of class. So let's try that later. So any other number, not 0 or 1? 0.25. So I heard a 0.2 and a 0.3, so I'm going to average. We liked maybe the uniform is what people are saying. Let's just use the uniform prior. So the beta 1 is uniform. And let's flip the coin 10 times. Good. There's true P. That's 0.25 right there. If you can't see it, this is 1, that's 0. So the scale's pretty good. There's my prior. It's uniform. And I've even normalized it. So I'm going to flip the coin once. Boom. We saw a 0 pop up. So that's what that was. This is the likelihood function. It's 1 minus p. Boom. I multiply it by 1, and my posterior is right on top of it, and you can't distinguish those two things. So there's a dotted line and a solid line there. So that's what a beta looks like for one coin flip. It's linear. That's kind of cool. So what that says, I kind of really like this, is it placed 0 mass right there on 1. That's the only place this is 0. So it says it can't be 0 mass on 1. Flip the coin again, boom, this thing starts curving a little bit. 1 minus p squared is what that looks like. Do that again, all of a sudden I've seen another draw and it ended up putting something else on 0 because now we've seen it. So that's kind of cool. And that's what that beta looks like. So it's extremely flexible. So it first looked linear, then it looked quadratic, and now it looks like something that maybe I wouldn't have imagined. So I flip the coin again, now this is highly skewed. So lots of flexibility. So keep flipping it. So I see a 1, it pulls it over to the right a little bit. That kind of makes sense. And I keep flipping my coin. And that's my posterior at the end of the day. And so there's lots of uncertainty in here. So what I might think in spirit is the answer somewhere around here. That's what P is. And so I don't think P is over here. I mean, there's some probability over here, just not there and not on the endpoint. Everything else is fair game, but it's vacuously small compared to everything else. That's how a Bayesian is. So that's what a Bayesian's really doing. And so they're going to construct all their inferences off of this posterior. So you might be thinking, well, maybe I think that P is that high point right there. So the mode of the distribution. That could be some answer when we get to chapter 7 and do decision theory. That's brought about by some loss function. I might think the mean of this distribution that's going to kind of pull things over just a little bit more is a good answer. Maybe I think that the median is a good answer. So we'll talk about all of those, but the Bayesian is giving you a full distribution of answers to quantify uncertainties. So I want to spend about 10 more minutes doing this simulation, see what happens. We can entertain Alan. So see what can happen in these degenerate cases. But you already know what will happen in that case. Why I think you're asking. So it's kind of cool. Anyway, we'll come back to this, see how this posterior evolves if you want to download the code and have a look at it yourself. Let's see. So that's what a Bayesian's doing in spirit. This isn't the best prior in the world, and I'll tell you why, but it didn't seem to do anything too bad. So it's kind of reasonable. I think it's intuitive, but there are better priors in frequentist sense. So if I ended up trying to build intervals off of this, by chopping off like maybe some portion of that and some portion of that, I probably would chop off 2.5% over here and 2.5% over here because this thing is skewed. So, but I would chop off some amount over here and then chop off some amount over there that adds up to 5%. I probably want the highest density region. If I use a different prior, maybe those intervals cover at some optimal frequency range. There is a prior like that. So, and that was proved in the 70s. So I'm not quite sure why in the 90s, and I was going to college, that they said Bayesians and frequentists don't like each other because there's certainly a lot of overlap. And I think a worse answer for this sort of thing is to invoke asymptotic normality on X bar. I think this is a much more sensible answer. What you'll notice is this is starting to look more and more normal, but it's not normal yet. So we'll talk about that when we come back. Thanks, you guys. I'll see you on Friday. Actually, I'll see you hopefully tomorrow night at 6 p.m. And we can go a little bit later if you want next time. So I don't have to be anywhere until, say, 9 o'clock. We can go for 3 hours. We'll try to keep it to about an hour.